Okay, now remember in the theorem which tells us the general behavior of power series. In the third case, we said the endpoints must be checked separately. So a natural question that comes out of curiosity is, do all cases of endpoint situation hold? So it diverges at both endpoints, converges at both endpoints, converges here and diverges here. So we have 4 cases. So I'll give examples that all those 4 cases can occur. So this is also going to be an exercise in checking power series for convergence. Okay. So this is let PQ be two real numbers. So positive, negative doesn't matter. So we are only interested that one of them is larger than the other. So this will define an interval. Okay. So find power series with the following properties. Okay, so or rather, let me say find power series. Okay, let's go to the interval of convergence is, okay, so first it is PQ. Okay, so it diverges at the endpoints. So B is diverges at P but converges at Q. C the other way around, P, Q, and D, it converges at both endpoints. Okay, so it looks like a miracle, but when you start doing these things, it will be very easy. Okay, so before you start, you should develop a strategy and work towards that strategy. If it doesn't work, then you revise your strategy. So what we, for these cases and also for these ones, we are hoping to get help from harmonic series. Okay, so here it will be alternating harmonic series. Here it will be just the harmonic series. And for this case, we just change the sign, maybe. Okay. And here we expect that the behavior at the endpoints will be like 1 over n squared. So alternating 1 over n squared and non-alternating 1 over n squared will make it converge at both endpoints. So let's see if we can do this. So the picture will be something like this. I have P here. Okay, so P here. I have Q here. So the middle point, let's use M for this. So instead of writing this all the time, so P plus Q over 2 is going to be M. And this length, so this is the radius of convergence, L. This is equal to Q minus P over 2. Okay. So M is the center. Okay. M is the center of the power series. And L is the radius of convergence. Okay, so we'll consider power series whose center is M, radius of convergence is L, such that at the endpoints these behaviors will be recovered. Okay, so let me start with the first one. So for A, I suggest that we look at n equals from 0 to infinity, x minus m to the power n divided by L n. Okay, so what do you say for this one? Is it going to satisfy the first property? when I write it like this, you are fooled. But simplify it. You see, I'm taking everything to nth power. So this is actually a geometric series, right? So this is, notice that this is summation n equals 0 to infinity x minus m over l. Everything raised to power n. Okay, so this converges if and only if the absolute value of the general term is strictly less than 1. It diverges everywhere else. So in particular, it diverges at the endpoints. Okay? So this is a geometric series. Converges if and only if x minus m over l is strictly less than 1. So diverges, so, so its interval of convergence is PQ. Okay, because at the endpoints, you see at the endpoints, this number is equal to plus or minus L, so the absolute value will be 1 and it will diverge. Okay, so this case is covered. B, okay, so here I suggest this one, summation n equals 0 to infinity. So let me write it in a way that will convince you. I will have minus 1n. Since I want convergence at one endpoint, I should try an alternating series there, and the sign will then shift for the other one. Okay, so here I have, and since I'm interested in this one, okay, so this one converges, okay. If what I'm going to write here does not contribute to a conflicting sign for this one converges. Okay? If this part also contributes minus 1 to the power n, this will be cancelled and I'll have 1 over n diverges. So I'm trying to play with this one to get convergence at the endpoints. Here I have, being a mathematician, I look at the previous case. Okay, so the previous case, this worked. Okay, so I try it. X minus m over l to the power n. Okay. Okay, so this is not a geometric series anymore, but when you do ratio test, okay, so the contribution of this will be 1. 1 over n plus 1 divided by 1 over n, the limit will be 1, so it will not tell us anything. But this one, in the limit, if you say, for example, okay, take the nth, use the root test, so this will give you 1, and this will go away. So the absolute value of this must be less than 1. Okay, so it gives me the same thing here. And I check the endpoint. So the interval of convergence includes this, maybe endpoints, just from this part. At the endpoints, when I put this endpoint, so the Q, okay, when I put this endpoint, okay, so this becomes Q minus M is equal to L. That's the length of the that's the distance from Q to the center, divided by L1. So this part will not contribute anything. And at the end point, when x equals P, x equals Q, the series will be this one. Okay, so it converges. If I put P here, then this is going to be minus L. So this side will give me minus to the power n. I have another one. So the series will be just harmonic series. It will diverge. Okay, so this is for B. So C. Okay, so again, look at the previous case. In the previous case, it diverged here, converged here because of the sign contribution of this. Okay, so I just make a conflict of signs. So instead of making this n, I make it n plus 1. Okay, so this will be summation n equals 0 to infinity minus 1 n plus 1, 1 over n, x minus m over l to the power n. Okay, so the same arguments, except that when this contributes... okay, so let me check if this is as easy as I... Suddenly I got... okay, so here I don't want this sign. Okay, So the sign of this is enough. Okay. I think when I put also m plus 1 there, no, this is okay. Okay, so this one, I just removed the sign conflict here. Okay, so the only sign is contributed by this. When x is equal to q, this is n, so this gives me 1 here, 1 over n diverges. So it diverges at q. When I put x equals p, this is minus l divided by l, so this one gives me minus 1 to the power n. It becomes alternating. Okay, it converges here. Okay, D. Now this one, again I go to the previous case. Okay, so in the previous cases, now I want this thing converge at the endpoints. What made this diverge at the endpoints was this harmonic series. Okay, so if I make the sign of this alternate, it converges, otherwise it diverges. Now here I want a term which converges regardless of sign. Okay, so I make it n square. Okay, so this is summation. So this is summation n equals 0 to infinity. Well, here, okay, let's make these things 1, 1, n equals 1, 1 over n square, x minus m over l, n. Okay, so this now converges at the endpoints. Okay, so well, this tells us that all these possibilities hold. So when you are investigating a power series, you should check the endpoints, because nothing is guaranteed about the endpoints with the general check. The general check is you use the ratio test or root test and find conditions on on x to make this convergent, but it gives you convergence and divergence at every point except these two endpoints. Okay, so the next question is the following, which you should be able to answer immediately, but this sometimes such a question appears in the middle of something very complicated, and then we start thinking about it. So is it possible to find a power series converging only on, say, 0 to infinity? If we draw the picture, maybe it will be easier. So this is 0, the function converges here, and it converges everywhere here. Okay, can you write a power series which converges here? Power series. Yes, but it's a power series, right? So what do we know about the general behavior of power series before you go into very deep questions about gamma functions and other things? Let's start from the very elementary properties. If they don't work, then we'll go step by step to more complicated things. So what was the general behavior of power series? Well, as luck would have it, it is here. The power series behaves only like this. So 1, 2, 3, in which category is this? It's not the first category because it says it converges for all x, but there are key points where it doesn't converge. The second category says it converges only at one point, but it converges at many points. So it must be the third category. So then, where is the center of this? There is no center here. Okay. So this cannot be the interval of convergence of any power series. Okay. So the first thing we tried worked. So your Maclaurin series, you missed a small detail there. Okay. So the answer is no. No. Check the theorem on general interval of convergence of a power series can be one of three cases, and this doesn't fit into those cases. So that's the power of theorem saying that only the following 5 or 6 things can happen. Okay. So this was a nice example. Let me see if there is another interesting example like this. Okay, we did this one. We did okay, so let's now look at the next topic, which is representations of functions as power series. Now, of course, we are interested in power series as mathematicians. It's fun, but they are also useful. They explain functions to us. Given a power series, obviously it describes a function, but that's not very interesting because we already have some nice functions which we use: sines, cosines, exponential, logarithm, okay, gamma function. So if we can express it as a power series, it will be helpful because you see, okay, nobody wants to add infinitely many terms, but if it's a convergent power series, the general term goes to 0. So after a while, the general term will be negligible in our calculations. So if you add only the first few terms, few depends on how precise you want to be, you will obtain a value for the transcendental function, which is otherwise not possible to calculate. Okay? So our first step towards that is to start with some known expressions of functions with power series and see what we can go from there. So first thing is the geometric series. Okay? And after that, next week, we will start directly from a function and construct a power series associated to that, called the Taylor series. And then we'll look at techniques of finding the number of terms to add so that to obtain a certain value of a function with a certain precision. Okay, so that will be the final technique, and maybe the last thing we do, or while we are doing those things, is to calculate the number e to any precision we want. I mean, e will be equal to sum of infinitely many terms. So how many terms should we add so that the 6 digits or 5 digits after the decimal point is correct? Okay, so that will be all we want to do this semester. So let me start representing functions with power series. Let's call this 1 because here we'll start with the usual power series. We'll start with the geometric series. So 1 over 1 minus x is equal to 1 plus x squared. The general term is n plus, and this falls for x less than 1. So every time you write a power series or you read a power series, this part is an essential part of the power series. Okay, so this tells us this thing makes sense only for these x. If you attempt to put larger numbers there, okay, so then you don't get equality anymore. Okay? Now what we want to do is we would like to integrate, differentiate both sides to get different functions. Okay, so suppose we are allowed to take the derivative of this. You see, the derivative of this side means that you put a big parenthesis here, put big parentheses here, and then you take the derivative. If it is possible to say that that is equal to the derivative of this plus derivative of this plus derivative of this, then life would be very easy. Okay, and that's why I keep saying that calculus is easy, because that's allowed. Okay. Okay, on this side you see taking derivatives is easy. starting from this power series, you obtain another power series freely. But the interesting thing is on this side, if you take the derivative of this or integrate this, you get different functions. So you already have a power series expression for this new function. For example, if you integrate this, you get ln of something. Okay, so for that ln, here you have an expression. Okay, so can we do these things? So that's the general theorem. So let me say the main two. So the main theorem here is the following. I will not prove this theorem. I will not even mention the general idea of this because it is a little bit long. You have to control the tail of this. Of course, if you stop here, you can, obviously, it's a polynomial, you take the derivative of this term by term, plus here you have something, and you are also trying to find the contribution of this. Okay, so there are some nice epsilon delta arguments showing that the tail's contribution is negligible. Okay, so if you want to look it up under the term uniform convergence. Every series which converges uniformly can be term by term integrated and differentiated. But that's too long, and we are not going to use the techniques that are used in the proof somewhere else. For the previous one, I gave you the idea of the main proof because what we do there are also used in other problem solvings. But this one is, let's say, technical. Okay? The power series can be integrated and differentiated term by term. Okay, the meaning of this is the following, that is, if f of x is equal to summation or, okay, let's do this like this, n equals 0 to infinity, cn x minus x sub 0 n, then I take the derivative of this. Okay, so remember the derivative of this means this one. So I take the derivative of the whole thing. Okay, so the theorem says, so this part is the theorem, this theorem. So this is still equal to, if you take the derivative term by term. So if you take the derivative of this, n comes down, you have cn x minus x sub 0, n minus 1. Okay, so this is the theorem. And similarly for integration. Okay? And similarly for integration. Okay? So again, if I want to integrate this, I'm integrating the whole integral series. So there's an integral sign. The question is, term by term integration means that can I take this integral, can I change the places of integral and summation? This is an infinite sum, so this is a limit of the sequence of partial sum. Integral is again a limit of Riemann sums. So this is one of the main problems that is studied in advanced calculus. Can you interchange the places of two limits? Under certain conditions, you do, and otherwise, if you take first this limit, then this limit, you obtain a number, you change the places, then take the limit, you obtain a different number. Okay? So you cannot change the limit. Doesn't mean that somebody will shoot you if you change the limit. If you change the limit, you will probably not get the same answer as before. So that's what it means, you can't do that. Okay, so for this, let us now apply this. As I said, such things are generally true in advanced calculus because there is this concept of uniform convergence which we need to study for another hour. Okay, so well, another thing is about endpoint behavior. The radius of convergence is the same. The radius of convergence does not change. So that's, of course, one of the most important things. You integrate something term by term. Now it converges on a smaller set. That will be a problem because you have to find that smaller set separately. But here the theorem says that the radius of convergence will not change, but the behavior at the endpoints may change. Okay? When you differentiate, you may lose some endpoints. If the previous power series was converging at the endpoint, well, after you take the derivative, you may lose it. There's a chance that you'll lose it, but you will not gain anything. And if the integration is the other way around, okay? But we will not concentrate on that. After we obtain a power series, you have to check what happens at the endpoints anyway. Okay, so let's see what we can do with these things. So, okay, I'm trying to find our solution here. Okay, let's see. Okay, we start with the power series. So 1 over 1 minus x is equal to 1 plus x squared plus x to the n plus something like this. This is holding for x equals x less than 1. Okay, so for example, this is generally what we'll do. Put minus x for x. As long as the absolute value is strictly less than 1, you can substitute anything. Okay, so that's the meaning of this. So this becomes 1 over 1 plus x equals 1 minus x plus x squared minus x cubed plus something. And what do we have? Minus 1 and x and plus something x less than 1. Integrate both sides. Let's say from 0 to t. Okay, I'll then make t equal to x again. So what do we have on the here from 0 to t, 1 over 1 plus x dx. This is equal to ln 1 plus x from 0 to t. So this is ln 1 plus t. If I put x equals 0, it's ln 1, 0. Okay? So this is left hand side is this. Right hand side, 0 to t. I have this 1 minus x squared, etc. dx. So this becomes x minus 1 over 2 x squared plus 1 over 3 x cubed minus, and the general term is going to be n over n plus 1 x to the n plus 1. Okay? And that's the, and I integrate this from 0 to t. Okay, so I have t minus 1 over 2 t squared plus etc. Now the theorem says that these are equal. So this one and this one. Okay. The theorem says that they are the same. Okay, so theorem says these are the same. Okay. So we found now put x equals now put x equals what? T equals x. Okay? We have ln 1 plus x equals what? This one. X minus 1 over 2 x squared plus 1 over 3 x cubed minus. Okay? So the general term I have minus 1 and x to the m plus 1 over n plus 1. Okay? So it turns out that this is converging at the endpoint. So maybe what I said about this behavior at the endpoint is the other way around. Okay, so but you don't have to memorize these things because after you take the derivative of integral, you have to check what happens at the endpoint separately again. So you don't have to know whether differentiation loses an endpoint or not. Okay, so we have here, on the Moodle you will have these handouts, useful power series. So here I did the ln part. So here, since I integrated, as I said, well, if I remember this correctly, if you integrate, integration is nice, so it has properties. This one was converging only inside, diverging at the endpoints. After you integrate, it converges, it starts to converge at one of the endpoints. Okay, so this is for minus 1x less than or equal to 1. Okay, so we gained this endpoint. Okay, so one is tempted to say that if it converges here, I put here x equals 1 and I get this one. So that's how you will obtain ln 2. Okay, you put x equals 1, here it is ln 2, and you obtain this. Obviously, it diverges when x is equal to minus 1, because then this becomes 0. ln 0 is not defined. Okay, so what other things? Let's do arctangent. We can also do arctangent. Okay, let me do arctangent and then we'll stop. We'll continue from here next week. So again we start with the geometric series 1 minus x is equal to 1 plus x squared plus etc. Put minus x squared for x. Okay, as long as the absolute value is less than 1, we can do it, the same story. So we get this one, 1 plus x squared equal to 1 minus x squared plus x to the 4 minus, okay, here the general term was x to the n, so this is going to be minus 1n x to the 2n plus, and this thing holds for x less than 1. Okay, so did I do something here? Okay, so this thing is oh, okay, so anyway, so now integrate both sides. Because I integrate this side, I recognize this is arctangent, and in the arctangent, if I put some nice values for x, I can recover pi, and I will have an easy power series for that value of pi. So integrate both sides. From 0 to x. Okay, so from 0 to x means that first you integrate from 0 to t, and then you put t equals x. But now you are experienced, you are at the end of calculus, so we integrate both sides from 0 to x. Okay, so here we get arctangent x equals, on this part I get x minus 1 over 3 x cubed plus 1 over 5x5 plus minus, and I have minus 1n, 1 over 2n plus 1, x 2n plus 1, etc. So let me check the endpoints here, because the endpoints we have to check separately. Even though this converges only on the interior, after you integrate, this converges at the endpoints also. Okay, because at the endpoints, if you put x equals 1, this is an alternating series. If you put x equals minus 1, then the signs are all shifted. It is again an alternating series, except that all the signs are shifted. So this converges for all x less than or equal to 1. Okay, and again by a theorem of Abel, this equality holds even at the endpoints. So arctangent 1 is pi over 4. Okay, so pi over 4 is equal to arctangent 1. So you put 1 here, 1 minus 1 over 3 plus 1 over 5 minus 1 over 7. Okay, so you obtain a value for pi. Okay. Now this is an alternating series. Okay, so if you add only this many terms, the error you are making is less than 1 over 7. Okay, so this tells us that you can calculate the value of pi with any degree of precision, theoretically. But practically 1 over n becomes small very, very slowly. So you see 1 over 7 is a very large number actually. So if you want 2 or 3 digit approximation, you have to add this this alternating series up to 10,000 or something. Okay, so practically this is very slow. So you have to invent other power series which will calculate this fast. So finding fast converging power series is another art. Here, at least we show that theoretically we can calculate the value of pi to any degree of precision. Okay, let's stop here this week. Next week I'll continue from here and hopefully do Taylor series. Now we have this evaluation, so I'm going.